All right, let's dive into a classic computer science puzzle. We're going to tackle the rat in a maze problem. And in the process, we'll uncover a really powerful way of thinking that's used to solve all sorts of complex challenges.
But here's the real challenge. We're not just looking for one way out. Our mission is to find every single possible path from the start to the finish. So think about that for a second. How would you even begin to make sure you didn't miss one?
So let's meet our hero for today, a little rat, starting in the top left corner of this grid. Its grand quest? To get to the cheese over in the bottom right. Seems simple enough, right? Well, this maze has some pretty strict rules.
Okay, here are the rules of the game. Our rat starts at square one, and the cheese is at the very last square. It can move one step at a time, down, up, left, or right. Now, the ones you see are open paths, like hallways. The zeros, those are solid walls. And here's the most important rule. You can't visit the same square twice on any single path. That's to stop our rat from just running around in circles forever.
So, faced with these rules, what's the first thing you might try? Well, probably just charge ahead, right? Keep moving forward whenever you can. But as we're about to see, that simple plan is going to run into a very, very big problem. All right, our rat's first idea is pretty simple. Just keep plowing ahead. So, first move, a confident step down. Looking good so far. Let's try going down again. We're making progress.
Okay, can't go down anymore from here, so a quick turn to the right. The cheese has got to be close, right?
And we're stuck, totally boxed in. A classic dead end. So that whole just keep moving forward strategy, yeah, that's not going to cut it. So what's a rat to do now? We need a much, much smarter plan.
And this is where the real magic happens. This is the aha moment of the whole thing. We're going to introduce a super powerful idea called backtracking, and it's going to change the game completely for our little hero.
So what exactly is backtracking? Well, simply put, it's a strategy where you try to build a solution one piece at a time. If you make a move and it leads to a dead end, like our rat just did, you don't just give up. You literally backtrack. You go back, undo that last choice, and try a different one instead.
You can really see the difference here, right? The bad plan is forgetful. It just barrels ahead no matter what. But the better plan, the backtracking plan, is smart. It has a memory. It remembers every single step it took. So when it gets stuck, it can just say, oops, wrong turn, and go back to the last place it had a choice.
Honestly, the best way to think about it is like having a magical undo button for every single move you make. Every step our rat takes is just a guess. If that guess turns out to be wrong and leads to a dead end, it just hits undo, and poof, it's right back where it was, ready to try a different direction.
Okay, so this undo power is a really cool concept, but how do we turn it into an actual, reliable strategy? Let's build a formal, foolproof master plan that will guarantee our rat explores every single nook and cranny of this maze.
So here's the rat's new thought process. On every single square, it does these 5 things. First, it checks if the move is safe. Is it still inside the maze? Is it a wall? Have I already been here on this trip? If it's safe, it marks the spot as visited. Then, it explores all the possible directions from there. If one of those directions eventually leads to the cheese, fantastic, we save that path. But, and this is the absolute key, step 5. After it's done exploring from a spot, it unmarks it. This is the backtrack. It's basically pretending it was never there, which opens that spot up for other potential paths to use later on.
Yeah, a quote from the source material really just nails it. It says, "When the recursive call is over, I come back and remove the visit. This is backtracking." That's the whole game right there. You explore one branch of possibilities completely, and when you're done, you clean up your tracks so it doesn't mess up the next branch. That's our undo button in action.
Now, to keep things organized, a rat needs a consistent order of operations. It's not just going to pick directions at random. We give it a priority list. It will always try to go down first. If it can't, it'll try left, then right, and only as a last resort will it try to go up. Following this strict order is what ensures that we find all the paths in a nice, clean, alphabetical sequence.
So, we have the rules, we've seen the epic fail of the simple plan, and now we've got this robust, backtracking master plan. It's time to put it all together and watch our little hero finally crack the maze code.
And success, look at that. By applying the backtracking algorithm, the rat successfully found not just one, but both of the valid paths to get to the cheese. Each letter there just represents a move. D for down, R for right. It's a perfect, complete, exhaustive search.
So the crucial takeaway here is that backtracking's undue power is what prevents the rat from ever getting permanently stuck. It systematically explores every single possible path to its conclusion, whether that's success or failure, and then it unwinds its steps to try the next alternative until absolutely nothing is left unchecked.
Of course, being this thorough, well, it comes at a cost. This kind of search can be incredibly time-consuming. That crazy-looking notation on the screen is just a formal way of saying that as a maze gets bigger, the number of paths to check can explode exponentially. It really shows just how exhaustive this search is, but also why for enormous mazes, backtracking is powerful, but can be pretty slow.
And that really brings us to the core of it all. This undue power, this ability to explore possibilities and backtrack from dead ends, is a fundamental concept in computer science. It's the same logic that can solve a Sudoku puzzle, figure out the most efficient schedule for a massive project, or even power an AI trying to win a game of chess. So it leaves you with a final thought. What other complex, real-world puzzles could you unlock if you just had a magical undo button?